All right, let's get started. Thank you for coming here today for this session about seamless mobile real-time communication with the WebRTC. Just a few people more, yeah. So during this session, we are going to talk about WebRTC and how to use it in a mobile app specifically. But before that, if this works, yes. Let me introduce myself a bit. So my name is Renaud. I'm a freelancer. I'm based in Paris. I'm also part of and a member of the Paris Android user group. First time in DroidCon Lisbon for me, so I'm very proud of being here today with you. Why this talk? I had the opportunity last year during a freelance mission for a client in video games, actually more cloud gaming, to work on WebRTC. So last year during the mission, I was able to set up a Compose multi-platform application or project and deploy it in a gaming solution for cloud gaming using WebRTC. I discovered things, and this talk is about sharing the things that I discovered. A bit about WebRTC first. WebRTC stands for Web Real-Time Communication, and it's a technology that enables real-time communication directly in your web browsers or your mobile application. The development and adoption of WebRTC has marked a significant evolution of web and communication technologies. With WebRTC, peers actually can stream video, audio, or even arbitrary data, binary data, which is very useful for cloud gaming when you send, for example, arrow up or left or right, this kind of data. First, the WebRTC, it's great to understand its history. So let's have a step back a bit and let's look at how the story began with WebRTC. In 2009, the concept of real-time communication within browser and without, yeah, you can join, and without the need for plugins started gaining traction around 2009, 2010. And Google played a significant role in that period. They acquired Global IP, GIPS, in May 2010, and it was a company known for developing high-quality voice and video processing data. In May 2011, so Google announced the WebRTC project, and it open-sourced its key components. This move was just to make it standardized, so a technology that has a standard, and it make it freely available to developers and inside browser vendors. So the W3C, the World Wide Web Consortium, and the IETF, the Internet Engineering Task Force, began working together with Google, of course, and also you will see some big companies, on working on a standard and making sure that the API and the protocol are all standardized, respectively. The W3C focused on the JavaScript API, and the IETF work on the underlying layers of the protocol and the data formats. It's working? Yes. 2012, Mozilla and Google started implementing the WebRTC inside their browsers, Firefox, Chrome, and this period marked the beginning of the practical experimentation and usage of WebRTC in real-world applications. 2014, WebRTC began gaining traction in the industry. Various startups and also established companies integrate WebRTC inside their solution into their product for video conferencing. File sharing also on real-time data exchange. In 2015, that technology matured with improved stability and performance. We discovered services like Appier.in, or now it's known as Whereby, if you heard of this software, and a lot of video conferencing tools showcasing WebRTC, like Google Meet. 2018, the W3C published the WebRTC standard 1.0. it marked a significant milestone in the development of WebRTC. So by that time, WebRTC was already seen widespread adoption in various domains, including the telehealth, online educations, some customer support, and other social media. I have to... 2020, sorry, until now. So of course, there was the COVID. The COVID pandemic accelerated the adoption of WebRTC because the demand for remote communication skyrocketed. So platforms like Zoom, Google Meet, Microsoft Teams, for example, they saw a massive usage of leveraging WebRTC inside their offerings. That was the part of history. So now let's speak about how does it work under the hood, the architecture. How is WebRTC architectured? And let's dig a bit into the standard and the way things are working with WebRTC. But for that, we have to understand architecture with several clients. You might have heard of mesh architecture. So in a mesh architecture, all participants are directly connected to all other participants. So this solution has some advantages. It's easier to set up with a low operation cost, and it requires high bandwidth, which is a disadvantage. It requires high bandwidth for each client to make sure that they all communicate together. In a graph theory, a graph where each node is connected to everyone, it's called a complete graph. So you can see this kind of graph here with 3 clients. For a complete graph with n nodes, 3 here, there is this formula n multiply n minus 1 divided by 2. So you will see that it keeps increasing. So this model is not scalable if we're all of us connected inside this room. So that's great when you're calling one person or 2, but then we have to switch to another architecture. This is the multi-point conference unit. You have client A, client B, client C. What the solution is to put a server and then to connect directly them inside the server. So this solution requires high computational cost for decoding and encoding on the server side the stream and then dispatch it to all the other clients. It brings high latency at large scale because you have to have a server that is strong enough to dispatch all the stream. So for WebRTC, how does it work? So we have seen mesh, we have seen the multi-point. Let's say we have client A wants to talk to client B and we have a server on top. So the client A, he creates an offer, which is kind of its ID, and to a signaling server. The signaling server will relay it to client B, and the client B, as you have seen, receive the offer, which consider this as his ID. Then the client B creates an answer, send it to the signaling server, the signaling server relays it to client A, and client A receives the answer. So after that, since they know each other, they are going to send what we call ICE candidates. It's ICE candidate exchange between the client A and client B through the signaling server, and both are actually gathering their ICE candidates information. So it's basically how are we going to talk to each other. Once this is done, the ICE candidates are sent to the signaling server related to each other peers. So now we have client A and client B in a peer connection. We don't need the server anymore. Nice animation. So basically, to my opinion, the process of establishing a WebRTC connection between 2 peers can be divided into 2 major phases, as you have seen here. First, the signaling phases. This is the phase that involves the exchange of connection information, when I was saying about the ID, for peers to connect directly. So this phase is not handled by the WebRTC standard itself. We're going to see that after. It requires an external signaling server or mechanism that we can actually create ourselves, so it's not part of the standard. And then there is the peer-to-peer connection phase. So this is the phase that involves the actual establishment of the peer-to-peer connection, enabling media and data flow directly between the peers. We spoke a bit about ICE. ICE stands for Interactive Connectivity Establishment. It's a technique that combines two things, a stun and a turn server to discover and also to establish the best connection path between WebRTC peer connection or WebRTC clients. This is where it enables real-time communication and challenging also the network environment. If we are not on the same network, for example, or if I'm speaking with someone in South Africa, for example, from Asia. So it involves the stun, which is basically a protocol that is used to discover the public IP address and also the port of a client. And then we have the turn server that act intermediaries when direct peer-to-peer connection are not possible due to restrictive network configuration. So basically the stun and the turn relay media streams between the client, and also they ensure that there is a reliable connection. So this is the complete graph of the architecture. So basically you have the NAT here that goes to the stun server. I think I can pin some, yeah. And also go to the turn server, the stun server. So you might have heard of Google is actually providing a turn server. There is also Twilio that you can use for free to discover the public address. Some information I would like to share before that. So the specification of the API, as I said, we have the specification of the ICE server. We do not have in the standard the implementation of the signaling server. It's not part of the standard. The WebRTC also transmit data using UDP, so the user datagram protocol. UDP is connectionless. That means that there is no formal connection between data transmission, and also the packets are independent, can be sent to any route, and also we don't have acknowledgement. So we can lose some packets sometimes using UDP. But that's something that's important to share when using WebRTC. If you want to have fun and go on a Google Meet or open a WebRTC connection, I found that there is this link that you can directly open in Chrome, and you will see everything that is happening between your WebRTC connection. That's very useful to better understand what is coming under the hood. Okay, so as we have previously seen, the signaling server is not part of the standard, but also it's mandatory to establish the connection between two peers to make sure that they are going to connect. Usually, a signaling server is solved or created through a regular HTTP-based API. We can create a REST API or whatever RPC mechanism that we want. So basically, the web application can relay the necessary information before the peer connection is installed. This is the diagram. Sorry, it's something that I try to generate it, so it's not perfect visually, but it's how it works under the hood. So basically, client A speaks to the signaling server to initialize the WebRTC, client B as well. Then we create the offer that we have seen before. We're going to set within the standard our local descriptor to generate an offer. We're going to send the offer. The signaling server will relay the offer. The client B will receive the offer, set his remote description from the offer, then create an answer, set the local description from the answer, send the answer. The signaling server will relay the answer, then we receive the answer. So at the moment, it's not so complex. It's a lot of coming up and back. Then that's the phase with the ID I was talking about. And then the second phase is about the ICE candidates. So the signaling server will receive your ICE candidates, relay them, So client A and client B will both receive the ICE candidates from the relay server. And when it's done, and when we had that, when we had that, then we are able to establish a pure connection between client A and client B, and we don't need the signaling server anymore. The truth is, actually, when you see this diagram, you're like, okay, why we are not able to achieve this? So why not achieve this together as Kotlin engineers? So I suppose, sorry, but why not create our own signaling server together right now, so you can better understand how to establish a connection between client E and client B. So for those who know, I'm quite fond of Ktor. Might have, maybe it's shared with some of you in the room. So let's write this in Ktor, since we are Kotlin engineers. If you want to learn a bit, I wrote some articles about Ktors, how to set up a web server using Ktor, if you want to see that. I also put some article about Material 3 if you don't want to do backend. So let's go and start to create our signaling server. Let's go to startktor.io, and for that, it's better to have a WebSocket because it's fast and easy to set up. So I had the plugin WebSocket. We will also need, we will see later, but it's more for scalability, encoding and serialization. So we are going to use the serialization from Kotlin X. So I add it as well. Now this is from the field. What we could do is, okay, the client is sending me some text. Why I'm not distributing it to the client? Client A is sending me some text. Why I'm not sending back to client B? Just plain text. Actually, you will see that it could work, and we're going to see that it works, but it's better to wrap everything inside what I call WS WebSocket. You can call it whatever you want, but wrap this inside a packet. So what I'm going to do, what I did actually, is you put an ID with the messages and also the data as a string, and you wrap and you make sure that it's always WS packet or your interface on top. And the WS messages is for now an enum. We have errors when we gather the ICE candidates, ICE server, the init, answer, offer. So this is for now what we need. Also, signaling server. What we would like to achieve is client A sends me some information, and as a WebSocket, I want to distribute it to client B. So I'm not going to do a ping pong or send it back to client A. So it's better to make sure that I know all the connection to my WebSocket and distribute them to the kind of a router. So for this very simple way, ensure that it's thread safe, of course, and put an ID with an atomic integer and put just a name. So what I did is just I put a name and a value here. And I'm using the Ktor object called default WebSocket session. That's it for the setup. Now it's Ktor. What we are going to do is install the WebSocket. This is from the manual. We say the ping period, the timeout, the max frame size, the masking, everything is by default. But also I'm adding the content converter because I want to serialize and deserialize my WS packet and not transfer just plain text. Then create a pool of connections. And in Ktor, for those that are familiar, there is this routing DSL, and let's create a WebSocket with /connect. So when someone goes inside, I'm just going to register this connection, and then directly I do the try with the finally make sure that you remove the connection at the bottom. And then you have many ways to do it in Kotlin. I put the more simple way to understand that, just basically while true. And then when I receive, I deserialize them, and then I'm doing something. What is something here? For very basic one, I'm just going from the connection, make sure that I'm not going to send to the one that actually sent it to me to relay it, and then send the data. That's it. So that's it for the signaling server. The two things that happen here is that we don't send any data to the other one, and we're going to cheat a bit here because as you can see, I send directly the data. I'm not processing the WS packet because I want to put that very simple for now. This is the moment where you are all afraid, but don't worry. What I said before is WebRTC was designed for web browser. And I'm not a web engineer, but actually since there is standards and everything is inside browsers, it's actually very easy to create index.html with a bit of JavaScript to actually create a client, client A and client B, using my my WebSocket, my signaling server. So what I did, there is my local video, my remote video, a start call button, my URL with my /connect, and then the peer connection, the remote connection, the local stream. As easy as it is. Then we just wait for handle offer, handle answer, handle ICE candidate, and then depending on the WebSocket, what I can do is set up the media device. It's perfect. Everything is inside the browser, and since it has been around quite a few years, you have I mean, every user are going to have a navigator that works with this implementation, and then you use the ICE candidate and you put the element for the view. Same for handle. You see, it's very simple code actually, and the remote one. Sorry. So what I'm going to display now is we're going to start the signaling server that I just showed you, and I split a bit. What I will do is I will create one page with the local and one page with the remote. So I'm just going to change that in the document. Okay. So this is a Ktor project. We have this section that I showed you. I put some debug. So let's start here. So, okay, so one thing, I cheated a bit because it's on my network, local network, so everything is on my machine, right? If I wanted to go on an extra network, it requires more job, of course, with the TON server and with the stun server as well, to discover the IP address. But everything is handled directly inside the web standard, so actually it's just setting default value, and you can point to the Google stun server, and then that's fine. Okay, let's go. So I put right here. It's just with the remote, and the left is just with the local here. So you will see how it works. So let me open. And you're going to see that. Okay, so this is me, and this is another So this is the remote. So what you're going to see is like, okay, is it two camera? So no, it's not two camera. It's two different streams, and since it's a local network here. You might be like, oh, it's just rendering this camera. No, actually, since it's inside my network, it's using the nice connection. But if you look deeper, you will see that on the left, on the right, sorry, the encoding not as perfect as here, because here is using my front camera, so full resolution, because it's how it does with the local web browser. On the remote side, it transfers to the pure connection between the two tabs. So if you look deeper, you will see some difference. Anyway, you can see the latency is perfect because, of course, it's on my network, but it's a pure connection. So even if this tab is in South Africa, it's going to work very well as well. Because it's a pure connection. So as soon as I have good network in South Africa, for example, then it's going to be fine. So it was as easy as this, setting up the signaling server, and as you've seen, there was some exchange here. So I received the ICE candidates at some point and sending some frame. And now, since I was speaking, it's the ping, sorry. But you see the candidate, the exchange, everything, the offer has been here. So everything was exchanged and routed directly to the other component. All right. Let's start the presentation. That was the demo. So, Android now. Now that we have our signaling server, let's have a look on how to use it in Android, because I spoke about mobile app. You have probably heard of third parties SDK allowing you to easily set up a video conferencing. This page is getstream.io if you are familiar with. There is LiveKit as well, so they wrap everything. Be sure that LiveKit is actively maintaining WebRTC SDK for Android. So as Android developers, we could directly use the WebRTC, so it's called libWebRTC or this fork from LiveKit if you want to do it by hand. It is a bit, you have to dig a bit in the documentation if you're using this one directly. All right. Return from the field. After digging with this, you have seen my previous sequence diagram with back and forth, so in synchronous, callbacks, etc. So in a client-server communication architecture, the state machine or asynchronous calls are two different paradigms, and this is the way they manage interaction and workflows. To my opinion, state machine is best suited for scenarios where the workflow is complex. It's a bit complex here, involve multiple states, and require a clear state transition. So during the peer connection, from the peer connection, to the WebRTC and going through the signaling server, sometimes things are evolving in a complex way. So I would recommend you to always think not in asynchronous. I ask for I send an offer, I'm expecting an answer. No, what you should do is, okay, I'm just having a state machine. What happens when I receive an offer? I do that. What happens when I receive an answer? I do that. So it's a bit different, but believe me, it's more scalable and more flexible, especially if you want or if your project manager want to introduce new features. So for example, we will see that a bit later, but what if the signaling server was injecting some things to your clients? How do you handle that? Well, you can create a new packet and handle this as a new state, for example. So for Android, this is the architecture I will recommend. So you have a WebSocket data structure. It's in charge of communication to the signaling server. It's open, close the connection to the WebSocket. Can be used to maintain also the ping session. We have seen that inside Keto, it's for free. And also, as I said, can be used to inject specific command if you want. Then I will put aside another data source, the WebRTC data source, that's in charge of the peer connection. The peer connection is the object, the main object in the WebRTC SDK. It's in charge of creating, receiving offer, answers, setting up the ICE candidates, negotiating the RTC configuration, the stun, the turn server. From the two data sources, what I would do, I would combine the flow from both data sources, product a state that your app will use. So I put that in a connection repository. You can call that a connection use case if you want. But basically, it's going to challenge the fact, am I paired to someone else? Am I connected just basically to the signaling server? What is my state basically? And this is where all the logic will come. And then, to be used by your UI, you can inject event from the user, like mute this one or disconnect or start the call to produce a new connection state, for example, or receive some command from the peer. Okay, let's have a look a bit. I have a bit more time, yeah. Let's have a look on the WebSocket data source. So we use Ktor server for our signaling server. Why not using Ktor client for our client? Basically, it's quite easy to set up. It's just here, install the WebSocket, and again, install the content converter. So what I'm going to do, I receive the messages, my WS packet, which I deserialize. And on start, of course, I'm having this open WebSocket session and make sure that, everything is set up. And then, I can take this one. So the session is here, we can close and send messages, and voila. Also, I put it on purpose WS, but it's better to put WSS as secure if you want to be secure. And then that's it. That's Kotlin. I have a flow, so basically I'm ensuring that session is active, and when it's active, I'm sending my WS packet, and when I receive a flow of WS packet, I consume it as a flow and deserialize it with a timeout if I didn't receive on time. For the WebRTC data source, so again, we need a peer connection, which is the object from the WebRTC standard. In my purpose here, I have a data channel. I was saying that before there was audio, video, and also arbitrary data. So if you want to send data, it's through the data channel. So in our case, we're just going to use video and audio, but if you want, you can put it here. Then ensure that there is a job as well to be sure that you can close it every time. And then that's it. There is the connection state, the as candidate state. This is part of the data channel if you want to send arbitrary data. And then we already have some callbacks. And what I'm doing, basically, I'm going to state in, and it's going to be sent directly to my connection repository. This is how to create an offer, the answer, the RTC configuration, that's to make sure that it works outside the local network. And closing, and here I was speaking about the stun server from Google. So the RTC configuration can be the default one, or you can specify the stun, or you can use Twilio stun. We started with Google, it was okay, but we used Twilio and it appears it was a bit faster. And the connection repository, I said that I'm going to combine actually all the states, all the value from the WebSocket and the WebRTC. So what I'm going to do is just I have a state flow. I'm combining my peer connection state, my WebSocket data stream, and actually, depending on my packets, I do some challenge. Here, if I receive some iServer, then I will set up the iServer, make sure that I create an RTC configuration, set this configuration, send back the ICE candidate. So it's all the things that was asynchronous, but here we can see easily how to split them. So you can actually split that into different functions, but I put that for the purpose of knowing what to do when we receive this packet, for example. The ICE candidate, the answer, and then also I'm saying that I'm connected at the moment, so for my UI to make sure that it's a loading screen. And actually, it's not big, the feedback, just here. And sending the value will be just ICE candidate with the value. I'm just following the standard at the moment, so it's pretty straightforward. So that was for Android, but actually this part, what I've showcased you, works for multi-platform. So everybody knows multi-platform here. You have to have a library that works for multi-platform. And what I showed you actually was part of the great job of Alex Shapirov, because he's doing a lot of things bringing WebRTC to multi-platform. So since WebRTC is a standard, we can take the iOS SDK as well, because it exists, the Android SDK from the WebRTC Android, for example, and we can adapt them, and even from the JS, actually, we can adapt them inside the multi-platform library. This is what he has been doing, and you can contribute. He is very helpful. I had some issue with iOS, and he fixed that, and also we work together. It's a good guy. There is room for improvement, of course, because it's only Alex working on this at the moment, or debugging tools. But the library, we used it on production, and it works just more than fine. How does it work under the hood? He even used Compose multi-platform. So what he does, he created this expect video with a video track from the standard, the audio track from the standard, and then there is the actual. So in the actual, there is this Android view with a surface view, which is basic Android. And for iOS, he is using HTML video view with the content. And again, it's a part of the binding between iOS and multi-platform. So since it's a DroidCon conference, I wanted to do one thing, is showcase you how to do it on an iPhone. So I'm going to use my iPhone. Up. And there is a sample app. So it's Compose multi-platform with the video that I showcase you. And what I'm going to do, so here it's me on the local one. And I'm going to start a call. And here below, so it's like before I split it. So it's the remote one. And as you've seen, everything works on this iPhone. Okay, so you're a bit far, but there is the sound as well because we set up the audio track as well. So there is audio, video, and we can start a call and it works fine, and I can split everything. So Compose multi-platform is great for that as well. Up. Okay, what's next? We have seen that from the history, how is it architecture? We have seen how to do it in web, how to do it in iOS. So that's great, but what is next actually? What we've shown is that the peer connection in a mesh challenge, where there is actually client E, client B, client C. Once I get rid of the signaling server, everybody is in peer connection. As we said, it's not really scalable. So there is another way of doing this. It's the selective forwarding unit. It's basically, if you're on a Google Meet, we are just two in the call, then it's going to work. Once we are more than two, you will see sometimes that there is a glitch because they're actually switching the way of the architecture behind. And basically, so that was a mesh. So it's a lot of one. And then we have the server here. And what it's actually doing is that the selective forwarding unit, so let's put another one. It's called the SFU. So basically, it's a media server. It's the component that is capable of receiving multiple media streams and then deciding where these media streams should be sent to which participant. And actually, its main use is to supporting group calls or streaming broadcast scenarios to everybody. So SFU, they don't process the media, but rather just route around. As such, they consume a considerably amount of less CPU than their MCU, the multiple conference unit that we have seen before. And their performance relies heavily on the network throughout the client B and on the server to client C. There is a lot of benefits from using this component. We can bring simulcast. Basically, it involves sending multiple video streams of different qualities. So I noticed that client B has a bad bandwidth, so why not trying to make the audio or the video more compressed, so the data will be more easily received, and sometimes that you see the camera of the other participant is a little bit blurry. There is temporal scalability, trying to involve encoding on different frame rates as well, so not only compressing but different frame rate. We can manipulate the media data directly before it was sent or received, so it's called the insertable streams. It's not used for putting ads, it's just useful for custom processors such as end-to-end encryption, for example, to make sure that the connection is safe, or even adding some effects like the filters on the video, for example. And there is also the protocol converter, so if you want to convert the WebRTC to a streaming, like if you want to have this discussion, also send that live to your Twitch channel or YouTube, for example, there is some connection. So to speak about this WebRTC, we have seen there is GetStream, we have seen that there is LiveKit. So why do we have WebRTC companies? The business has increasingly evolved since the COVID, and the demand for reliable WebRTC companies, as I said before, has skyrocketed. While we use WebRTC to offer a powerful foundation for real-time communication, it has some limitation. We have seen that actually creating a signaling server is not so hard, but who wants to have to deal with this kind of network? So WebRTC company, they stepped in because they can improve the scalability and the performance, because it requires some kind of development. For security reason, we have seen that with the SFU unit. Also for customization and bring a better user experience. For example, when we need to put some filters, we need to put some subtitles, for example, and also to make sure that developers actually easier to set up WebRTC inside the apps. This is a list of the companies that I try to found that are actually building their business on WebRTC, so it's big and there is a lot of money. There is many use cases of WebRTC. There is, as I mentioned, telehealth, to give healthcare to people around. There is HR tech, fitness as well, social media. I mentioned gaming, of course, creating some events with friends, or even dating apps. So there is actually a lot of use case of using real-time communication around the world. So what's next? To sum up, as we look to the future, the integration of AI on machine language technologies in WebRTC is set to kind of revolutionize the user experience. With innovation like real-time language translation or subtitles, you have seen that demo of someone speaking in Portuguese and it's already translated to the other guys in English, for example. Noise suppression, if I'm on a coffee shop, there is a lot of noise, then they can process and remove the noise. Also, video enhancement filters, the possibilities are endless, and this is why also they are putting this effort, this company, to bring more effects inside their solution. All right, so I hope I've shown you today that as a Kotlin engineers, we have the tools, the capabilities to achieve this kind of incredible things across iOS, web, Android, of course, whether even in WebAssembly for the future. And also, we're able, as Kotlin engineers, to do some backend stuff. So our skills today, and this is my conclusion, I think are more relevant than ever in this evolving and it's rapidly evolving landscape. So thanks to you for this talk. And let's continue to push the boundaries of what's possible with WebRTC together. Thanks.